In this video, we're going to demonstrate that the inscribed angle created from two symmetric chords is half of the central angle for the same arc. So we're going to start with circle A. Okay, we're actually going to do this using the two-proof table, two-column proof. Okay. We have both our statements and our reasons. We are given that we have circle A, and then we're going to start building upon that. We're actually going to list the other givens, which are the symmetric chord piece, which we're actually just going to draw here really quickly. We're going to arbitrarily pick a point on the edge of the circle and call it point B. We're going to create a chord. It doesn't matter what chord we create. So we're just going to draw from one edge of the circle to another, to point C. We do need it to be symmetric though, so we need the other chord to be the exact same length. Recall we do that using our compass for measurement. We don't use the ruler. So we capture the distance between B and C using the compass. Okay. Keep the compass point at B and draw an intersection segment between the two circles. That forces us to have two congruent chords. Okay. Since we have two congruent chords, we know that it's going to be symmetric about the line joining A and B. Okay. So we now also want to create the lines that cause the central angle, the two radii from AC, so segment AC, and segment AD, which is the other intersection point, down here. Okay. So we have beta, the angle in here is beta, and then the angle in here is alpha. Okay. Where alpha just corresponds to the central angle and beta corresponds to the inscribed angle. And what we're trying to demonstrate is that alpha is equal to 2 beta. That's the point of this proof. Okay. We're given basically our construction that we have seen here. I'm just going to label as construction rather than writing all the details of point B, congruent chords BC and BD, and then the two radii. Okay. So it's just our constructed piece that which leads to the starting point. Okay. Since it's a symmetric chord, we can draw a line through B and A, okay, which bisects the angle. It's an angular bisection. Okay. So we have two angles here and here. This is going to be 1/2 beta, and this is going to be 1/2 of alpha because it was an angular bisection. Okay. So the statement is that we have 1/2 beta and 1/2 alpha as shown from an angular bisection. Okay, so that's the reason why we have those. Okay. We're going to use a theorem that we have not yet shown nor developed, one involving triangles. We are going to use the theorem that a triangle has total internal angles, the angles that are inside the triangle, of 180 degrees. So we're going to say that 180 degrees is the sum. This is a shorthand symbol for sum of the internal angles. Okay. That's the theorem that we're going to use. We're also going to use another one which says that the angles opposite congruent sides of triangles are themselves congruent. Okay. This is the isosceles triangle theorem. We'll be demonstrating that later in this chapter, but it is necessary to use here. One can see that we have the triangle BAD, okay? And we're going to say that BA, segment BA, is congruent to segment AD, okay? Because they are both radii of the same circle. Okay? Because they are congruent and they make up part of the triangle, we do know that this angle right here is also 1/2 beta. Okay? And that comes from, we'll label these as Theorem 1 and Theorem 2, and just shorthand write Theorem 2 is the reason why we can say there's another 1/2 beta, which is that guy there. Okay. We use our first theorem and say that this angle right here is gamma. Gamma just looks like a vertical alpha. Okay. And we're going to say that 180 degrees must equal the measure of 1/2 beta plus 1/2 beta plus gamma. Or in other words, through simplification, 180 equals beta plus gamma. Okay. We are then going to say that, okay, we have a linear angle here because we know that we drew a straight line from B to the other edge of the circle. It just happened to pass through A. So we know that 180 is equal to 1/2 alpha plus gamma as the definition of a linear pair of angles. Okay. We then use substitution, or the transitive property, by saying that beta plus gamma being equal to 180 must also then be equal to 1/2 alpha plus gamma. Since gamma is equal to itself, we can, by simplification, get rid of it. We now have beta is 1/2 of alpha. If we double this, we have 2 beta is equal to alpha. This was just by simplification. On to the rest of the steps, which is what we were intending on proving in the first place. Recall that that is what is up here. Okay? So we have just demonstrated through geometric construction and through the two-proof table that the angle beta is going to be half as angular as the central angle. Basically, that inscribed angles are half the size of central angles so long as they subtend the same arc, where the arc here is CD.